Okay, so firstly, good afternoon, and firstly, thank you to Aspetar for inviting me here to provide this presentation, and also for providing an accommodation grant. This study is looking to investigate whether Hsp90α and glucose-regulated protein 78 are markers of an attenuated cellular stress response within human skeletal muscle. Okay, so exertional heat stress induces an increase in cellular temperature, oxidative stress, mechanical stress, and metabolic strain, and thus induces a cellular stress response. This is manifested as through an increase in protein denaturation, apoptosis, and in severe cases, an unfolded protein response. This can lead to increases in tissue damage, and systemic inflammatory response syndrome, and also then lead on to exertional heat illnesses. Hence, a delicate balance is required when we're trying to acquire a heat-acclimated phenotype, whereby we want to not obviously overdo it and induce exertional heat illness, but we want to obviously optimize adaptations. To achieve this, potential biomarkers we could use are the heat shock protein transcription of the heat shock protein system. Previously, Hsp90α has mainly been utilized to act because its role as a protein chaperone, chaperoning nature proteins and refolding them, and for its anti-apoptotic influence. A couple more genes could add to this information, including Hsp90α and Grp78. Hsp90α can do this through its extra roles in regulation of the cellular stress response and recovery via regulation of signaling kinases and generally gene transcription factors and regulation of gene transcription and protein translation machinery. And thus it also has a role in controlling protein synthesis. Grp78, which is located within the endoplasmic reticulum, has an important role within regulating the unfolded protein response, and thus through that it controls whether protein synthesis can be activated or whether it is inhibited. Therefore, the selection of these extra genes could better indicate an individual's thermotolerance and thus exertional heat illness risk, and could also provide some information perhaps because these are the characteristics of these genes perhaps could look at kind of recovery post-exertional heat stress. So the key cellular change that links exertional heat illness, cellular stress response, and exertional stress to the heat protein system is an increase in protein denaturation. This leads to an increase in transcription of these genes. And thus this is why they're potential biomarkers of exertional heat illness risk. Particularly of interest here is in vitro, when the heat shock response is inhibited, Grp78 is upregulated. Hence, perhaps in vivo, we may find that we thought we may find that Grp78 may be upregulated in cases where perhaps there are heat intolerant individuals. Obviously, the preferred tissue to measure this response in would be muscle biopsies, or in muscle due to skeletal muscles. It's obviously a higher thermal strain compared to other tissues we may measure HSPs in, and also due to their key role in locomotion. However, obviously, post-biopsy, there'll be a decrement in performance, so it's not ecologically valid. Hence, we require a surrogate tissue to measure the muscle response. Previous data from our group has shown that the leukocytes are a valid tissue to measure or show a similar response to vastus lateralis for Hsp72. Hence, the next step will be to measure the Hsp90 and Grp78 within leukocytes. So, overall, previously Hsp72 has been pretty much a gold standard for measuring thermotolerance. We now want to look at whether the responses in the VL for Hsp90α and 78 are similar, and then whether this muscle response is mirrored within the leukocytes. And then that can allow us to know whether these genes are useful for measuring thermotolerance. So, to do this, we first conducted preliminary testing, where we used a graded treadmill test to assess lactic threshold and VO2 max. and then completed a downhill familiarisation. We then completed hot downhill 1, which consisted of 30 minutes downhill running at the lactate threshold on a minus 10% gradient in 30 degrees centigrade and 50% relative humidity. We conducted this rather than just normal exertional heat stress, due to obviously it's unethical to do to induce exertional heat illnesses. However, if we can, by combining hot downhill running and exertional heat stress, we could induce a more severe stress response. And then post this acute preconditioning stressor, we then did a second stressor, which of an identical stressor, to see whether any change in physiological strain and the cellular stress response occurred. We measured rectal temperature, heart rate, and VO2 continuously. Hsp gene expression was measured before, post, 3, 24, and 48 hours post, and measures of delayed onset muscle soreness, quadricep tenderness, and visual analog scale of pain were completed pre, post, 3, 24, and 48 hours post exercise. So, physiological changes. Core temperature decreased by 0.3 degrees during hot downhill 2, and we also saw a reduction in heart rate of around 8 beats per minute. Visual analog scale of pain and quadricep tenderness were decreased 24 to 48 hours post-exercise, post-hot downhill 2, and there was no DOMS before hot down 2. So, there's a decreased thermal strain within hot downhill 2, which is equivalent at least to core temperature, with a reduction with a partial heat acclimation, and also a decrease in DOMS. Hence, there appears to be a reduced physiological strain, and thus it could be used to measure whether these genes are respond to reduced or markers of the cellular stress response. So, previous data we showed that Hsp92 increased following hot downhill 1 within muscle, and then was decreased during the second bout when the physiological strain was reduced. We then looked at this for Hsp90α, and we showed that the increase immediately post-exercise and 3 hours post-exercise occurred within the VL, and that when the physiological strain was reduced within the second bout, there was no response. During the, we then looked at Grp78 and showed a response, so an increase at 3 hours and 24 hours post during the first and second bouts of hot down. So from this data, we can suggest that Hsp72 and Hsp90α, but not Grp78, are biomarkers of the cellular stress response. So once we've determined that, we're now looking to see the leukocyte response. So as previously, 72 was increased during hot downhill 1, but then this was attenuated during hot down 2. We then moved on to Hsp90α, and we showed an increase immediately post-exercise and 3 hours post-exercise. But this increase during hot downhill 2 was attenuated, hence a very similar response to what we found in the VL. However, Grp78 didn't increase at all during either bout. Hence, 72 and 90α appear to be suitable surrogates for the muscle stress response, but Grp78 does not appear to be so either. So, overview of the results. Obviously, 78 isn't responsive to different physiological strains, but Hsp90α, like Hsp72, seems to be responsive within both tissues. This is a novel finding, both for Hsp increase in the VL and for the surrogate response within the leukocytes. Extra benefit is perhaps that this knowledge could provide some information in participants whether they recover quicker post-exercise and may be able to do exertional heat stress or perform better in subsequent bouts of exercise. And obviously, of course, it's a useful biomarker for the severity of the stress, and therefore thermotolerance and exertional heat illness risk. So, potential applications here is, obviously, we could now measure Hsp72 and 90α to infer an attenuated muscle stress response. This could be used pre and post heat stress test when fast redeployment to hot environments is required. It could also be used across heat acclimation programs to infer whether a thermotolerant status has been, or to infer thermotolerant status. So next future directions, obviously the model we used induced muscle damage, which or likely induced muscle damage, which could be a confounding factor for, or could maybe have some influence on the surrogate response. Hence, the first thing that would need to be done is to measure whether a surrogate response occurred in response to a bout which only induced exertion or heat stress. This should be done both acutely and across the heat acclimation program. Then, ideally, we'd then look into the physiological and molecular adaptations which occur within both tissues and perhaps any influence between the tissues that could be responsible for the surrogate status of leukocytes for the muscle stress response. So, thank you, and any suggestions and questions are welcomed. And I'd also just like to thank my supervisory team, Professor Mark Lewis and Dr. Lee Taylor. Thank you very much.
Thank you, James. Could you please clarify an issue? You started your introduction saying that taking biopsies could influence performance, and I thought that your rationale is that you were not going to take biopsies, but then you presented the data from the bastrolateral.
No.
So did you take both biopsies and then blood samples? No?
So we take both biopsies and blood samples. So from the biopsies to measure response, and then to find out. So basically, the whole crux of the study is do biopsies. So in the biopsies, do we get a stress response? And then if we get a stress response, is it mirrored within the leukocytes? And from that, can we then measure, can we use the leukocyte response in a more applied situation where you don't want to be taking biopsies to then infer whether someone was either heat acclimated or there's a thermotolerant, and obviously then risk of exertional illness, or potentially. No.
Okay, you wanted to validate your methods. Thanks.
Thank you, James. Very, very interesting presentation. One quick question, because you started talking about the heat acclimation phenotype.
Yep.
And then your exercise was only 30 minutes in downhill running at 35 degrees.
Yep.
And you showed a pre and post difference in core temperature of 0.3, but you didn't show the absolute temperature which they reached during exercise.
Okay. During the first bout of heat down 1, they reached 39.3 degrees.
In half an hour of downhill running?
In half an hour of downhill in hot environments. Second bout, it was down to 39.0.
Wow, that's quite impressive.
Yes, wasn't that nice.
Yeah, and I guess the other question you partly answered at the end there with kind of teasing out whether, because heat shock protein is obviously expressed with heat shock, but also with any stress.
Yep.
So the stress of running downhill for half an hour is quite an important stressor. So it'd be interesting, like you said, to kind of tease out which one is maybe the more important of these two.
Definitely.
I would have the same question as Julien, but not on the acute response, but on the difference that you observe from the exercise 1 to the exercise 2.
Yep.
How did you account for the repeated bout effect? Because if you do 2 eccentric exercise 1 week apart, we know that will be less damage on the second one, irrespectively of the heat.
Okay, linking that into the core temperature response. I guess you're looking just for the mechanisms, or just from the repeated bout, or between what might cause between the 2 bouts?
More on the repeated bout. So do you think that the difference, the small difference that you observe in the exercise 2 are specific to the fact that they were in the heat, or you would have observed the same thing without the heat?
Okay. From what the data we've shown, and we think it's probably mediated by reduced cardiovascular strain through an increase in plasma volume, which we haven't shown, which was about 10%. Again, I appreciate from the repeated bout, and obviously there's a potential pyrogenic effect on the from the muscle damage. The data which is showing that, so I think it's maybe the Montan paper, and then there's some data from Neil Walsh's lab at Bangor. They've obviously shown an increase in core temperature when exercise has been conducted during muscle damage. With regards to the pyrogenic effect, so increase, I think it's in interleukin 6, that only those studies showed it from about 30 minutes post to 7 hours later. So potentially, because it was an acute bout and the muscle damage wasn't already present at the start, it probably isn't pyrogen related. So it's probably an adaptation rather than a kind of thermoregulatory adaptation rather than an adaptation through reduced muscle damage. That's our group's thoughts on it.
So I was wondering about the stimuli for the upregulation of the hip shock proteins. And I wonder whether you are aware of any data where the same type of data have been collected in people that where you passively hit somebody and just collect data whether there's also an upregulation indicating that there maybe temperature is actually the primary stimuli, or many other factors related to the running and the muscle damage, what it is on the other hand, major factors for...
From passive heating, seems to be pretty conclusive in rodent models where this is increased, so 72 is increased with passive heating. Within humans, there's been a few studies from a few Japanese groups which shown it has increased, but then there was quite a good paper from James Morton where they, again, related it back to his 2006 paper and utilised used the same core temperature and same muscle temperature increases that they had shown during submaximal running. So I think it's about a 39 degree increase in core temperature and the increase in muscle temperature up to 40 degrees. And then they showed no change in, I think they measured 72 and a few other HSPs, so they showed no change in any of them. So again, it might not be that it's the heat stress per se, it's a stress that's occurring because of the heat stress, and maybe not totally insulated. But yeah, I'd probably hazard a guess that it's probably exertional heat stress and muscle damage related, the increase, just because obviously there's changes shown, but the heat stress per se on its own isn't. It's something that's with the interaction with exercise.
Maybe you have to isolate the leukocytes and just apply temperature to see whether just the temperature per se have an effect on
it definitely has been shown. That definitely does have an increase within the actual leukocytes itself. And it's the
Thank you very much for your interesting presentation. We move to the last presentation of this session.